gonna work. That seems to get the whole board in. Okay. Well, you know what? Can we tilt it up a little bit?
I don't know.
Oh, you know what? I know how we would do that. That should get more of the board. Okay. Just remember to write big.
I'll be right back.
Okay, so you've jotted something down in your notes. You have an idea about the question that's on the board. You all have protractors and rulers out, which you aren't really going to need today. How could you negate a vector of 25.5 meters to the east? Don't yell it out. Or you can jot it down in your notes so that you all have an idea. Jot down your best idea. I know you have lots of good ideas. How could you cancel out or negate 25.5 meters east? Okay, I'm gonna do shirt color lottery again. Shirt color lottery. Ooh, and I'm gonna use this. Okay, somebody wearing, oh, this will be funny, it's Farmer Day. Somebody wearing plaid.
Aww.
Well, I got you, you, and you. Wait, okay. Or somebody in, I'm going to cancel that. Somebody wearing either blue or gray. Nice try. Okay, so that would be Max, Mr. Taylor, Mr. Reese, Ms. Hall. One of you. How could you negate 25.5 meters east? Bingo, you got it. So, for vectors, we can cancel out any vector by adding its opposite. Okay? Anytime that we have a vector, we can cancel it out by adding its opposite. 30 meters north is canceled by adding to it 30 meters south. And some of you did that with your cards in the lab yesterday. You, took all your souths and your norths and canceled them out and said, oh, we only have to go 5 meters north. Or took all your east and west and said, hey, they all cancel. We're in a straight line. Okay, good. So anytime that we have, we can erase this now. Anytime we have a vector we can cancel it out directly by adding its opposite. We sometimes use the sign as a proxy for direction, and I'm going to give you back your tests today. We're going to get through this stuff, and then you're going to get your workouts back. Some of you saved your own butts on one problem. Your velocity to and from your trip to Boardman should have been, something north, something south. And some of you didn't put north or south, so you would have lost a point, except one was positive, one was negative. Okay, I'll give it to you on that. So we can use sign as a proxy for direction. We do that very often. Okay, when we add the negative of a vector, it's the same as if we subtract it. So 20.0 meters east plus 20.0 meters west equals 0, as does 20.0 meters plus a negative 20.0 meters. Okay? Those are equivalent statements. Okay. When we multiply or divide a vector by a scalar, so what's a scalar? Something that has no what? No direction. Only got magnitude. If we have 20, if it took you, let's use our 20 meters east here. If it took you 10 seconds to travel 20 meters east. So our delta t for this little journey is 10 seconds. Is 10 seconds a vector or a scalar quantity? Scalar. It's just got magnitude. There's no direction to time. Time is scalar. If we want to get the velocity for this trip, velocity, okay, somebody wearing black, velocity, somebody, so that would be Cody, you've just hollered one out. So I'd have Cody, Austin, Philip, Paige, or Josh. What's the velocity for the trip, and is it a vector or a scalar? Okay, Josh. 2 meters. So my velocity is, you're saying it's 2 meters?
Per second.
Okay, 2 meters per second east. Is that vector or scalar? Somebody in red. Yeah, it's a vector. So this is a vector. This is a scalar. We divide a vector by a scalar, and lo and behold, we get another vector. Okay? So when we've got a vector and we multiply or divide it by a scalar, we're going to come out with a vector. We can express vectors in terms of multiples. If you are doing this trip, so this is velocity of u. 2 meters per second is not very fast, folks. You're taking this trip and we want you to hurry it up. Double your velocity. Your new velocity can be expressed as 2 times velocity of u. Okay? So you can express something that has, when you have changed something like that, you can express that quantity as a multiple of the vector. Okay? You can slow down. You can have 0.5 velocity of u. And the example on the board is 3 times as fast as v turtle is 3v turtle, which is still pretty slow. Okay, we're going to talk about coordinate systems. We started this conversation yesterday. Whee! You're all quite familiar with the Cartesian coordinate system. Okay. When we are doing vectors, we use the Cartesian coordinate system. By convention, we sort of impose this 2 different ways. One is what we've already been doing with our delta x's and delta y's, where delta x, our x-axis, this is along the surface of the Earth. Okay? Delta y, then, our y-axis, is typically up from the surface of the Earth or down under the surface of the Earth, or off of cliffs or into holes or anything like that. Okay? We also tend to use this coordinate system with the cardinal directions. So if we're talking about something where we have no direction, we don't have north, south, east, and west, we have surface of the ground and going up into the air, surface of the ground going down off a cliff, jumping off of anything. We'll have stuff kicked off of tables and pushed off of cliffs and thrown off of bridges before this chapter's over. You know, this is all just delta x, delta y. The other thing that we do is we kind of impose this coordinate system on the compass, and we will tend to use north, south, west, and east imposed on a Cartesian system. You can use a coordinate system. You can line the coordinate system up just about any way you want. However, before you go getting all excited, it really helps if you stay consistent. And to stay consistent, you'll hear me say very often, by convention we do this. Which means in all of physics, in this physics class, when you take a physics class in college, if you go on to anything else, this is how it's going to be handled, because this is how we typically handle it in physics. So while you could get all creative, you probably just want to stick with what everybody else does because it makes it a whole lot easier. You know, I know you're all creative geniuses, but save it for something other than making up new coordinate systems in physics. By convention, of course, we treat this as positive, this as negative, this as positive, this as negative. And you know that. You've known that since you started graphing in, what, 3rd grade or something? So that's easy. You just have to be consistent. Okay. Let's start with some of our very simple, very straightforward resultant vectors. Solving them mathematically. Okay. So yesterday we solved we solved for vectors just graphically. You had a ruler, you had a compass, you drew your vectors to scale, you measured angles. Very straightforward. We're going to now do this using Pythagoras, our old friend. We love the Greeks. So, if we imagine traveling 20 meters north for some reason. And notice that I did not draw that carefully to scale. There was no ruler involved. I just sort of stuck a line up there. We're not doing this graphically anymore. So we still want to attempt to be close to scale, just because it kind of helps you mentally, but we don't have to measure these real carefully. Then I turn Gesundheit, and I head 10 meters east. I want to know what my resultant vector is. So we know from our experience yesterday that the resultant vector is going to be a line that connects the what of the first vector and the what of the second. Somebody wearing white or gray. Yeah, the tail of the first vector and the head of the last vector. So let's draw our resultant in. Okay, there's our resultant displacement, our resultant vector. You all know how to do Pythagoras. We know that this resultant squared will equal our delta x squared plus our delta y squared. And this is just a reworking of a squared plus b squared equals c squared. Okay? I find it particularly helpful to make sure that I refer to these as delta x and delta y, because that keeps it straight in my head. We're going to get to problems, you'll get to problems next week, I will not be with you anymore, where you'll have multiple delta x's and multiple delta y's, and if you've got x and y attached to them, boy, it helps with the bookkeeping. But so do colored markers and pens. Okay, so we know that r equals the square root of delta x squared plus delta y squared. Go ahead and solve for your resultant. Okay, I get a resultant that is equal to 22.36067978 meters. But that's not a vector. I need to have a what? Somebody in blue or green? Jess, you're in both blue and green. It must be your day.
What was the question?
This is, I've got this for my resultant, but it's not a vector yet. I have 22 point something meters. What do I need to make it a vector? I need direction. So what I need to find is that angle theta. Okay? I need to find that angle theta. Okay. In your notes packet, I put a quick little trig review of the 3 trig functions that we'll use in here extensively. I did not get the trig review sheet done yet. I'm looking for one. Sine, cosine, tangent, so, ca, toa. And they will be up forever and ever, amen, on the wall, above the board. If you ever forget your trig functions, they're on the wall. The tangent of any angle is equal to its opposite divided by its adjacent. And honestly, I'll tell you that until I get warmed up for the year and I've been using trig functions for at least a week, I draw little arrows for myself. You know, it's a visual strategy. If you're a visual learner, feel free to draw little arrows on your paper to the side opposite the angle and the side adjacent to the angle. Okay, so how can we find this angle? Well, we've got the opposite side, we've got the adjacent side. So we can take the inverse tangent. Angle theta will equal tan minus 1 of the opposite over the adjacent. Okay? In this case, that means that theta equals tan minus 1 of 10 meters over 20 meters. If you're using TI 30 XS's, second function button, tangent button, and then you just can enter, it'll put up a parentheses for you, enter 10 divided by 20, close parentheses, hit equals. What's your angle? Somebody, well, let's see, do you have anybody in yellow or orange? Okay, there we go. You all have a calculator out and at your desk, right? Because you clearly would not sit down in physics without a calculator at your desk. Good. I'm ever so relieved. Okay. 26.5650518 is theta. So what's our resultant vector, our final answer for this problem? How will we write this? Okay. Okay, we have 3 sig figs to work with. So R, the resultant vector, equals, you said 22.4 meters, Jason? And that is at a heading of 26.6 what? Degrees what? East of north. Okay? We are coming east from north. Okay? Those are pretty darn easy. It's Pythagoras and a tangent. I have a packet for you. I knew you'd be excited. Yay! Good fake excitement, Maddie. Okay. This is problem set 3A and 3B. 3A is all problems. Yasmin, can you pass that over to Mike? I can't get to their row easily. Yeah, that all goes to Mike. Okay. Let's try that. Page 3A is all problems like this. Now, on 3A, it's odds only. We are skipping number 5. Mr. Boggs had asked the other day, did we ever use the z-axis? No. Number 5 involves the z-axis. I really want to make sure that you're good with the x and y before we go twisting your head around the axle with the z. So once you get through all of them and you have them all right and you want to knock yourself out and go crazy and have fun, try number 5, that's fine. But do all the other ones first, please. 5 and 10, I think, both involve the z-axis. The answer key for this is posted on my PBWorks page, okay? Which is also where today's lecture will be on video. So if you need to go back and review anything we did in class, it'll be on the PBWorks page this afternoon sometime or tomorrow morning. Okay, extras, just leave them on the, there we go, thanks. Okay, so this is fairly straightforward, yes? We can do you want to do one more of these, or no? Let's move on to the other side of this. Okay, let's say we're actually given a resultant vector. So, I have somebody who is traveling 55.0 meters at 25 degrees north of east. Okay? So I tell you that, your friend is going to hike 55 meters at 25 degrees north of east. Is it true that in their motion, in their movement, in their displacement, there is an x component to their displacement? And a y component to their displacement? Is that a true statement? Yes. Can we figure out what the x and y components of their displacement are? By golly, we can. This process is called resolving. So, okay, we found the direction of resultant vectors. This process is called resolving a vector. So you're breaking it up into its component parts. The other way we're solving to find the vector, here we're resolving it down into its components. Okay, think about your trig functions. We're going to start off with sine. So, sine of any angle theta is equal to what? Page. Opposite over hypotenuse. Good. It's not cheating to look at the wall. That's why they're there. Okay. For this angle theta, where is the opposite side to this angle? Delta y. What do you know? Do we have the magnitude of the hypotenuse? Yeah, we do. So we can say, with a better marker hopefully, that the sine of 25 degrees is equal to delta y over 55.0 meters. True? Pretty darn easy to solve for delta y now, isn't it? So the sine 25 degrees times 55 meters is equal to delta y. Go ahead and find your delta y. What do we have, Allie? Yep. 23.244044 meters equals delta y. Okay. Can we find delta x? Sure. We have cosine. So remember that cosine of any angle theta is equal to adjacent over hypotenuse. What is the adjacent side to this angle theta, Savannah? Yeah, delta x. That's our adjacent side. So now we know that cosine 25 is equal to delta x over 55.0 meters. Okay, we can solve for delta x. Go ahead and find delta x. Okay. What do you get, Blake? 2829?
Yeah, 2859.
Okay. Good. So the x component of this displacement is 49.84, etc., etc. Okay, we can sig fig this out. We get what? 3 sig figs? 2 sig figs. 2 sig figs. So we would have, we're going to cheat and make it 3. We're going to call that 25.0. Okay? 49.8 meters is our delta x. Delta y is 23.2 meters. Okay? And this is, we said this was north of east, so this is 49.8 meters east, 23.2 meters north. Okay? If we had an airplane, so an example I used with somebody yesterday, you're driving an equipment truck for an airplane that's going to be dropping supplies, okay? Like international spy stuff. It's James Bond week, you know, it's the 50th anniversary of the first Bond movie. So you're driving the truck underneath Bond's plane. He's going to be dropping some valuable cargo to you. You can use this to resolve a vector of velocity as well. Let's do one like that, and then we'll do tests back. Okay. Bond has the plane. He's flying the plane at 32 degrees above the horizon, flying it up in the air, traveling at 227 meters. We'll make this 32.0 degrees. 22.7 meters per second. Your mission, should you choose to accept it, now that's mission impossible, is you have the little truck. And you want to drive this truck underneath the plane so that you stay directly underneath the plane. So that when he drops whatever valuable cargo it is, the bed of the truck is there to catch it. How do you figure out how fast you have to go to stay directly underneath the plane? Well, is it true to say that this velocity has an x component of velocity and a y component? Yeah. Guess what? Same thing we just did. All you're doing is resolving the vector. So we want to know the velocity on the x-axis. We typically denote that with v sub x. Okay? With our marker. Yeah, we'll dream about it. Okay, which trig function will we use here? We're looking at the angle, we're looking at the vector adjacent to the angle, so cosine. Okay, so cosine of 32.0 degrees equals adjacent over hypotenuse. In this case, that equals v sub x over 227 meters per second. We can solve for v sub x. Oops. Times 227 meters per second equals v sub x. Go ahead and solve for your x velocity. Okay. What's your x velocity, Austin Brooks? Okay.
All right, is that 22.7 or 220?
I'm sorry, 227. Did I say 22.7?
Yeah.
My apologies. $192.506 blah 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 blah. Sig fig, we would have 193. What are our units here? Meters per second. So v sub x equals 193 meters per second. If you're driving a truck under the plane, that's how fast you have to be going in order to stay directly under the plane. I think you better have jet packs on that truck. Okay? Fairly easy, fairly straightforward? Okay. The entire packet for 3B is these kind of problems. This is breaking down vectors into their component pieces. Sample problem 3B in the book is another one that is breaking down vectors into component pieces. Questions? Y'all feel like you can do these? You will have a quiz tomorrow. On your quiz tomorrow, you will have one graphical construction of a vector. You will have these are perpendicular vectors. These are solving perpendicular vectors. One perpendicular vector problem, which is Pythagoras and tangent. And one vector resolution problem. Okay? So three questions on the quiz. 3A, 3B, and the items from the book will be due on Monday. You should probably be able to get most of them done today in your study hall. Honestly, if you go in there and chug, I think you can chug away at them and be done. I think that's it, yeah? Okay, so we will now do tests.